Okay, everybody, this video is just going to be, it's going to go over 1-5 intermolecular forces. So I'm just going to go over the review notes with you, so the intermolecular force review notes, and then just kind of show you what to look out for, maybe stress some different vocab that you might see in AP chemistry that we don't tend to use in honors chemistry or chemistry 1, like the expression dipole moment. Anytime you hear dipole moment, just think the word polar. So if I ask you if a bond has a dipole moment, I'm asking you, is it polar? Which bond has the greatest dipole moment? It's which one's the most polar. What molecule has the greatest dipole moment? It's like which molecule is the most polar. So the phrase dipole moment, you can just switch it with polar if that makes more sense to you, okay? So just want to go over intermolecular forces, and then also I'm going to show you some questions on the Unit 1 Concept Check 2. Just show you some of the questions, the way they like to phrase things on the AP exam, and kind of what to look out for in terms of intermolecular forces, all right? So let's dive into it. So first off, let's understand this. So when we talk intermolecular forces, the first three that we should think about are the ones we learned in chemistry 1. So we have hydrogen bonding, dipole-dipole interactions, London dispersion forces. A lot of times, though, instead of London dispersion, they'll just call it dispersion. It means the same thing, London dispersion forces. Remember, dipole-dipole interactions and hydrogen bonding is basically the same force, the same exact thing, just hydrogen bonding is a stronger dipole-dipole interaction, and because it's so much stronger, we give it its own name. But really, all intermolecular forces come down to is Coulomb's law. The higher the charge of the opposite things, the opposite poles attracting each other, the stronger the attraction, and the smaller the radius of those poles, of the atoms that are interacting with each other, the closer they can get, the stronger the interaction. So that's really what it boils down to. Okay, so hydrogen bonding and dipole-dipole interactions are permanent forces of attraction that can be there in a molecule. And so hydrogen bonding and dipole-dipole interactions are only found in things that are polar. Okay, so the molecule itself has to be polar. Everything technically has London dispersion, and the more total electrons your molecule has, and kind of the more basic volume the molecule has. So if you have a really big molecule with a big electron cloud, the greater the London dispersion, okay? So these three intermolecular forces are strictly for covalent compounds. So we're talking about organic molecules interacting with other organic molecules, or just, covalent or molecular compounds. We will talk about an intermolecular force called ion interactions or ion-dipole interactions, and that's where we're going to kind of combine ionic bonds and intermolecular forces together. So we'll talk about those in a second. All right. But again, it comes down to Coulombic attraction. All right. So this right here, this is a carbon monoxide molecule right here, and this is another carbon monoxide molecule. Also understand, like, if I want to illustrate a intermolecular force, I have to show two molecules, at least in my drawing, or it won't be an IMF, it won't be an intermolecular force, right? Because we're talking about the force of attraction between molecules, not within a molecule. So let's differentiate. Like, this is a triple bond, right? This right here, this is a polar covalent triple bond. That's not an IMF. The IMF is this, these three dashes right here, and it's the negative dipole of this molecule interacting with the positive dipole of that molecule, and so that is your dipole-dipole interaction, okay? Not this, all right? This is just a polar bond. And so if I look at this bond, I know it's polar because the two atoms in the bond have an electronegativity difference. Okay, so within the bond, I know this side of the bond is going to have the partial negative charge, and this side of the bond is going to have a partial positive charge, because I know oxygen's more electronegative than carbon. And so this interaction between the negative pole of this molecule and the positive pole of that molecule, that's what we call a dipole-dipole interaction, okay? So we can look at water. Here's the positive side of a water molecule, and the oxygen's the negative side of the water molecule. So this interaction right here, this is called a hydrogen bond. Now, you might say, well, I thought it's the same thing as here. Here's the negative side of that molecule interacting with the positive side of that molecule. And it's right. That's right. This is the same exact thing. This is the negative side of this molecule, and this is the positive side of that molecule. And so that is a dipole-dipole interaction, but it's very strong, and it's much stronger than this, and that's why we give it its own name. This is called a hydrogen bond. This dipole-dipole interaction is called a hydrogen bond. Now, what makes it so special is it comes back to Coulombic attraction, right? So the things we have to know about fluorine, oxygen, and nitrogen is that they're very electronegative. These are the most electronegative elements. So when H is bonded, hydrogen is bonded to one of these, there's a very big electronegativity difference, which means the bonds are very polar. Now, what does that really mean? It means that this partial negative right here is higher in charge than, let's say, that partial negative, because this bond is not as polar as that bond. Not as polar means a lower partial negative charge, or more polar means a higher partial positive charge. So this negative is more negative than that negative, and this positive is more positive than that positive. So when these two molecules interact, there's going to be a stronger attraction because this positive is a higher charge than this positive in this molecule, all right? So that's one reason why these bonds create a stronger dipole-dipole interaction, so much stronger that we give it its own name, hydrogen bonding. But also because these are very small atoms. Fluorine, oxygen, nitrogen are very small. And so that means these molecules are actually going to be closer to each other than these molecules. So that means that these dipoles are going to be closer to each other than these dipoles, and that's going to also increase the Coulombic attraction, which makes it stronger, okay? Now let's understand, an HF polar covalent bond, an HO polar covalent bond, an HN polar covalent bond, those aren't hydrogen bonds. This is a polar covalent bond. This is a polar covalent bond. This is a polar covalent bond. In order to show a hydrogen bond, you have to draw at least two of the molecules and show the dipole-dipole interaction, right? That's the hydrogen bonding between water molecules. This bond right here is just a polar covalent bond. This interaction right here, that's the illustration of the hydrogen bond, okay? So here, this would be a polar covalent HF bond. The dashed line, the couple dashes in between the molecules, that is the hydrogen bond. So that's the hydrogen bond, not that. That's just a polar covalent bond, all right? So how do you know if you're polar with hydrogen bonding or polar with just dipole-dipole interactions? First of all, again, remember, the molecule itself has to be polar for it to be either dipole-dipole interactions or hydrogen bonding, okay? If they're non-polar molecules, they can't have dipole-dipole interactions and they can't have hydrogen bonding, all right? So if you're polar without a Fon bond, then this dipole-dipole interaction is called a dipole-dipole interaction. We wouldn't call this a hydrogen bond because these dipoles aren't a result of a Fon bond. This is H bonded to Cl. It's not H bonded to F, O, or N. Okay, so I know water's dipole-dipole interaction is called a hydrogen bond because it's due to a Fon bond, one of these bonds right here. I know that this dipole-dipole interaction is just called a dipole-dipole interaction because it's not a part of a Fon bond. All right. Now, London dispersion, it's kind of hard to illustrate, and so you're probably never going to illustrate it that much. But another way to think of London dispersion is a spontaneous or a non-permanent dipole moment. So it's when a non-polar molecule becomes polar for an instant, okay? Or so it's a non-polar molecule. So it's a molecule that doesn't have a dipole moment, all of a sudden having a dipole moment. So meaning all of a sudden becoming polar for an instant. And then, so dipole-dipole interactions can kind of turn on, but because they're not permanent, they turn off. So like here is kind of, let's say this is a nonpolar molecule, okay? Well, the electrons in the electron cloud around the molecule are not always going to be evenly distributed within the cloud. So at any given point in time, maybe more of the electrons are over here and less are over here. And same thing happens to this molecule here. So when I snap my fingers, if there's more electrons over here, this side of the molecule becomes negative and this side of the molecule becomes positive. Same thing happens over here. So all of a sudden, right there, right in that instant, I get a dipole-dipole interaction. The problem with this dipole-dipole interaction is it's not permanent like this, because this molecule is polar. This is always a partial positive. This is always a partial negative. So that interaction can always happen. Whereas this, the electrons could redistribute, and all of a sudden this interaction turns off. So it's a non-permanent dipole-dipole interaction. That's the way to think of dispersion forces. And the way to know if your dispersion forces are stronger is just if you have more total electrons. If you have more total electrons, or you have a really big molecule, you're going to have a greater opportunity for an uneven distribution of electrons, and that's going to produce more opportunities for what we call spontaneous dipole moments, or London dispersion forces, okay? So again, what we just illustrated, dipole-dipole interactions, hydrogen bonding, London dispersion, those are all within just covalent structures, just covalent molecules, okay, between different covalent molecules, all right? Now let's look at some other things that, again, boil down to Coulombic attraction. So we could look at ion-ion interactions. So technically this is called an intermolecular force, but it's kind of a misnomer because we don't refer to the smallest particles of ionic compounds, molecules. We refer to them as formula units, and then formula units are broken up into individual ions. So ion-ion interaction is another way to say ionic bond. And it's just asking, why is lithium bonded to chloride stronger than sodium bonded to chloride? Well, it's still going to come down to Coulomb's law. So I know that this is an ion-ion interaction, this is an ion-ion interaction. So it comes down to overall charge. Well, a +1 ion and a +1 ion, a -1 ion and a -1 ion. So the overall charge is the same between these interactions. However, we need to know that lithium is smaller than sodium. So these ions are actually going to be closer to each other in this structure. So lithium chloride is going to have the stronger structure. So sometimes we call it a lattice structure. So lithium chloride has a stronger lattice structure than sodium chloride. Or sometimes we just ask, which one of these do you think is going to have the higher melting point or the higher boiling point? And we would go with lithium chloride over sodium chloride, not because of electronegativity or anything like that, because this ion-ion interaction is going to be stronger than that ion-ion interaction. And it's just because we know that lithium is smaller than sodium. So this interaction is going to be happening closer. These ions are going to be able to get closer to each other compared to these ions. All right. And then we have something called ion-dipole interactions. And the way you really want to think about this is it's when salts dissolve in water. So when salts dissolve in water, so let's say I take sodium chloride and it dissolves in water, these positive ions get pulled apart and they get surrounded by water molecules. Well, water, the opposite charge sides of water are called dipoles. Okay, and so an ion-dipole interaction is where the negative dipole of a water molecule interacts with a positive ion, or I could have drawn a chloride ion, like a -1 ion over here, interacting with the positive dipole of a water molecule. Okay, so here is an ion, here is a negative dipole, so we call this an ion-dipole interaction. Here's another illustration of an ion-dipole interaction. Okay. Now, I know that lithium's ion-dipole interaction with water is going to be stronger than sodium. And again, it comes down to the radius. The charges are the same, right? Sodium's 1+, lithium's 1+. But because lithium's smaller, it can get closer to that dipole. So that interaction is going to be stronger, okay? So here we just got hydrogen bonding again. and dipole-dipole, and then London dispersion forces. Okay, so make sure you review those notes, those handouts you got, and make sense of it. All right, so let's get into some practice problems. And so this is on your concept check too. I'm going to go over some specific questions here. So let me get to that. All right, so I'm going to skip back to, let's go to number 9 first. All right, so here we got methane, ethane, butane. And this is just asking if the pressure in each of these containers were to increase, which one will condense at the lowest pressure? So a couple things to take from this. This is asking, the way this question is set up, it's asking which of these have the strongest IMFs, which of these molecules exhibit the strongest intermolecular forces. Because the stronger the IMFs are, the further the molecules can be away from each other to then connect and condense back to the liquid state. So the gas that will condense at the lowest pressure is the gas that has the strongest IMFs. So here we have 3 hydrocarbons. And remember, by definition, we're going to call hydrocarbons nonpolar. So methane's nonpolar, ethane's nonpolar, butane's nonpolar. Okay, so which one of these nonpolar molecules has the strongest IMFs? Well, their only IMF is London dispersion. So the butane is going to have the strongest IMFs because it has the biggest molecule. It has the most electrons. It has the biggest cloud. So the answer to that's going to be butane. Okay, and it's not letting me choose it, but okay. It's just because so I'm just in the preview mode. So butane there. All right, number 10. It says the London dispersion forces are weakest for which of the following? Okay, so they're all nonpolar diatomics except for xenon, which is just a nonpolar atom. And it's just which one has the weakest London dispersion? It's the one with the least number of electrons, so hydrogen. Okay. Let's check out 11. All right, so here we have a bunch of diatomic molecules. You can notice that they're probably an element because there's no difference between this ball and this ball. Maybe if they had different colors, you would know they were different atoms, but because they're the same size and the same color, we can assume that whatever this is the same as this. So maybe let's call it hydrogen. So H bonded to H, or maybe F bonded to F. So we know we don't have any polar molecules here. So the only interaction that we could have between the molecules is London dispersion forces. And it says, which of the following best describes how the model is limited in the depiction of the phenomena? So it says the above diagram is a molecular molecule of a gaseous diatomic element, so we know it's nonpolar. That is just above its boiling point, so it's all been vaporized. Intermolecular forces between the gas molecules will cause them to condense and into a liquid phase if the temperature is lowered. Which of the following best describes how the model is limited in this depiction of the phenomena? So it's like it doesn't show the dispersion forces. So let's see. So it's not about ions, so we know it's not there. We know it doesn't have permanent dipoles because we know it's nonpolar. It does not show how the temporary fluctuating dipoles. This is another way to say London dispersion. Temporary fluctuating dipoles. So non-permanent polarity. That's London dispersion. So the answer is D here. Okay. So let's keep going. Let's go to number 12. All right. So this is just asking which of these best describes ethanol as a solid. So remember, molecular and covalent mean the same thing. So you could say organic, but none of the choices are organic here. So we would say it's a molecular solid, but because it's not just a hydrocarbon, because we have a functional group, it's polar, and it has an OH bond, so it has a fond bond, so it has hydrogen bonding. So it's a molecular solid with hydrogen bonding, so C. All right, and then I also wanted to look at 13. All right, so here we got a big molecule, nonane, but it's all just carbon and hydrogen. So this is nonpolar. So it only has London dispersion, but it's a really big molecule, so it has a good amount of London dispersion. Here we got a smaller molecule, but notice some of the hydrogens are actually fluorines. So this is a polar molecule. Okay, so this has dispersion forces, but it also has dipole-dipole interactions. Now, it doesn't have hydrogen bonding because the fluorine is not bonded directly to hydrogen. So the fluorine is bonded directly to carbon. So this just has dipole-dipole interaction. Now, if I wasn't given this chart, I might think that this probably has a higher boiling point than that because this is polar with dipole-dipole interactions and this is nonpolar with only London dispersion. However, when we look at the chart, notice that nonane has a higher boiling point. So all that means is its London dispersion is stronger than this guy's dipole-dipole and London dispersion. That's all that means. Okay? So which statements helps that observation? All right? The carbon chains are longer in nonane than in there. So it has greater London dispersion. There you go. That's the answer. Okay? There you go. C. All right? So I also wanted to look at 17. All right, so here we got ionic radius. All right? And it's asking, based on Coulomb's law and the information in the table above, which of the following cations is most likely to have the weakest interaction with a water molecule? So the weakest ion-dipole interaction. So we're looking for lowest charged ion and bigger radius. Okay? So it's either gonna be, so the biggest radius is sodium or calcium. We're going to go with the sodium because, yes, it's a little bit smaller than calcium, but it's only a +1 ion than the calcium. So they have a similar size radius, but since sodium's only 1+ and calcium's 2+, we would expect sodium there to have the weakest interaction. All right, let's go to number 19. All right, so notice HF has a much higher boiling point than F2, and we already know the reason. HF has hydrogen bonding, where F2 only has dispersion forces. But HF has a much smaller electron cloud. So how can you have a much smaller an electron cloud, but still have a higher boiling point? It's because this molecule ends up being polar. So it's one that's talking about weak dispersion forces in F2 versus hydrogen bonding in HF. So D. Liquid F2 has weak dispersion forces only, whereas HF has both the dispersion forces, not as many dispersion forces as F2 because HF has less electrons than F2, but it has hydrogen bonding. So that's why. All right. And then I wanted to go to 26 if we can. All right. So we have liquid A, liquid B, liquid C, liquid D. Notice that liquid C has the most particles in the gas phase at the same temperature. So that means liquid C has the weakest IMFs. Okay, because at the same temperature, more particles were able to break those IMFs and escape to the gas phase. Okay, or I guess another way to think about it is the higher the vapor pressure at the same temperature, the weaker the IMFs. So of the pressures in these flasks here, this would have the greatest pressure because it has the most gas particles there. So highest vapor pressure means weaker IMFs. So just real quick, all of these are hydrocarbons. Which ones would be expected to have the weaker IMFs? It would be pentane because it has the least amount of carbons and hydrogens. So it has the weakest London dispersion forces, and it would be which of the following is not shown in the model, so we don't see it in the model, but best explains why flask C must contain pentane. It's because it's not showing the strength of the intermolecular forces, but we know it has the weakest based on what's in there, okay? But it's not showing the IMFs. So C, not showing. All right, and then I wanted to go to 28. All right, so this one is a good one. It's asking you to find the hydrogen bond. So remember, you need negative dipole to positive dipole, but one of those dipoles have to be off a fond bond. So here's nitrogen, but it's not bonded to hydrogen. Okay, but that's okay. It would be a negative dipole here. And it is interacting with hydrogen of this molecule, but notice this hydrogen is not attached to fond. It's not attached to F, O, or N. Okay, and here's oxygen. That's a negative dipole of this molecule. But again, it's interacting with a hydrogen from that's bonded to carbon, not fluorine, oxygen, or nitrogen. So that's not a hydrogen bond, and that's not a hydrogen bond. Here we got to be careful. This is negative dipole to negative dipole, so that interaction isn't any good. That's not going to happen. And then we have nitrogen interacting with hydrogen, but again, the hydrogen is not part of a fond bond, so not a hydrogen bond there. Here's H bonded to H, so that doesn't work. So here, we got a negative dipole, oxygen, interacting with hydrogen from another molecule, and that hydrogen is attached to F, O, or N. So there's a Fon bond, and it's interacting with a negative dipole of the opposite molecule, so that is a hydrogen bond right there. And then here's another hydrogen bond. Okay, here's a Fon bond, here's a positive dipole of the Fon bond, and it's interacting with a negative dipole of that molecule, so there would be a hydrogen bond, so choice D. All right, so then let's go to, I wanted to do 35. So largest dipole moment means most polar. So this is pretty polar. This is symmetrical, so nonpolar, nonpolar, nonpolar. So it comes down to CO and HF. And we just have to use our periodic trend. There's a bigger electronegativity difference between HF than there is CO. So even though they're both polar, this one is more polar. More polar means largest dipole moment. So D. And then I also wanted to do 39. All right, so here we got water, and they want us to kind of find the hydrogen bond. So let's understand, choice A, that would be a polar covalent bond. That is not a hydrogen bond, right? You got to show the interaction between molecules. This is within a molecule, so it doesn't count. This is negative dipole to negative dipole, so close, but no, that would actually be a repulsion there. And then here's positive dipole to positive dipole, so again, that would be a repulsion. What we're looking for is negative dipole to positive dipole, and that is there. So choice D is the correct way to show a hydrogen bond in water, okay? Our hydrogen bonding between water molecules, all right? Okay, so hopefully that helps with some IMF stuff, and hopefully you can go back and adjust your answers to that concept check if you haven't to some of them, and yeah, we'll keep moving forward.